my name's Umesh Vazirani. I'm a professor here at UC Berkeley, and I'm also the research director for quantum computing at the Simons Institute, where we are speaking right now.
What is your general idea around quantum breaking, public key encryption? And because you have been working quite actively about that, and actually you were one of the first, because I saw you have a paper from 2012, so very early. So if you just tell us a little bit, because we were talking about how did you get in quantum, but particularly in quantum cryptography.
After my 1993 paper with Ethan Bernstein, we were thinking about how powerful quantum computers could be. We knew that they were more powerful than classical computers. But at that time, we were trying to explore whether you could solve actually NP-complete problems as well, which would have been in one shot, solving, not just breaking cryptography, but doing much more. And then in 1994, so we were unsuccessful. All our attempts were unsuccessful. And in 1994, we sort of formalized this into a way of saying that, in fact, there were fundamental reasons why we think that quantum computers will not solve NP-complete problems. So this was with Ethan, but also with Charlie Bennett and Gilles Brassard. And in that paper, we also showed that that not only was it that even though quantum computers could be very powerful, there were certain things they couldn't do. But among the things that they couldn't do, we showed is they could not invert random functions. And this was, to us, an indication that you could do cryptography that quantum computers could not break. So this was the first indication that there might be something like a post-quantum cryptography. And in parallel with that, Peter Shor gave his algorithms for factoring and discrete log. So, this was, these beautiful insights that showed that the basis of classical cryptography, these were the two most important problems whose security classical cryptography was based on. And Peter's algorithms just broke them.
So you had this two sides of a coin, or a bifurcation. You said, here's something we think is interesting that seems to pose a challenge for this type of computation. At the same time, look what this computation can do. Like what a polarized era of discovery, but early and exciting. Oh, that's cool. That's really cool.
Yes. And then I think it was about almost almost a decade later, around early 2000s, Oded Regev was a postdoc here with me, and he was working on trying to get a quantum algorithm for solving lattice problems. Now these are hard problems. And there was cryptography that was proposed based on lattice problems, but it was not, but there were some shortcomings. And in the process of, again, he reached a point where he realized that all his methods would break. There was a certain reduction he was trying, and at some point he realized in order to make this algorithm work, there was one crucial piece, and he couldn't get it to work. And then he had a brilliant idea, which was to say, well, maybe this piece is really hard for quantum computers. And that little piece is called learning with errors. And that's the crypto system. And in the process of saying, well, maybe that's hard, he actually showed that it's really hard. This was a quantum reduction, saying that if actually lattice problems are hard for quantum computers to solve, then this piece is really, really hard.
Yeah, it's the new foundation of like what is difficult for.
It was a new foundation. It gave a new kind of result about lattices that was not known before. It showed that lattice problems were much harder than people realized, or that this problem, inherited sort of in the average case the difficulty of lattice problems in the worst case, and this was a really interesting new step in the process.
What is your impression about the development? Because there is also a lot of hype around, especially the computation, the computers that are built. And every now we read news, this is going to take another 5 years. We need this number of qubits. And even with that number of qubits, it will take a week to have that public key broken. But at the same time, we're actually also exploring this idea that's not about only computing, but it's math. And so the idea that there might be also a new logic that might emerge from quantum mechanics, quantum computing, and then this new math might accelerate, also post-quantum cryptography, but for sure the breaking of the current cryptographic systems.
Yes.
What do you think about it?
Well, so let me say first of all that I tend to be skeptical about all this hype and about these very optimistic predictions. So I've been historically very, very skeptical about it. I think that there are two things happening now that are somewhat different. One is that there's a lot more effort that's going into building quantum computers and doing it in novel ways. That's the one thing. But the second thing is that there's also a lot of effort that's gone into really optimizing algorithms. So, before when these algorithms were, when we did not have the computers to implement them, there was really no incentive to sit down and say, well, here's clever ways to actually reduce the time by a factor of 2 or a factor of 5 or a factor of 10. But people have been doing that, and in fact there was very recently a paper by Craig Gidney where he put together many new ideas that have come up in the context of factoring, which improve, on a practical level, how long it would take to implement, how many steps it would take to break, say, RSA 2048. And based on both of these, I would now, I'm now ready to believe that, I would not be surprised if that were to happen within 10 years.
Right. And also because so far we have only Peter Shor algorithm, which is already a few years ago. But any other algorithm might pop up anytime at this point because by working on this and knowing better the logics, the algorithm, the math behind, there might be even a shorter way.
Well, actually, so this is what these, the new estimates are based on. There are really new ideas on how to improve the efficiency. So at some level you can say, well, the basic outline of the, what makes the algorithm work at a very abstract level is the same. But if you look at the new pieces that go into it, these are extremely clever. There are really new ideas there that speed it up.
Do you think it would be safe to say it's something like the feedback loop of actually working with some of the earliest ideas and seeing how it shakes out in implementation, or just put it into use? Feedback loops we have all the time when we actually begin to work with new ideas and sort them out. It's that feedback loop that might be allowing us to see, this could be better, this needs to be better, this isn't quite what we wanted from it, or is that
I mean, there are, it's sort of, there are many, there are many parts you leave unexplored because they're just not that, and in early days you're sort of just trying to map out the.
You actually want to go all the way around at least once, right?
Yes. So, and there are always hidden, gems that you leave unexplored.
Cool.
you're working a lot on post-quantum cryptography and also new ways of new systems and methods for sure. Let's say, so you're working on that because anyway you expect that those systems will be available also around 5-10 years, or what is your time frame?
Well, you see, I think what's been clear for a very long time is that, you know, cryptography has this thing that the threat of breaking it is already sufficient to act. And so it's always been clear that well before the first, you know, the quantum computer scales, it would be prudent to act and switch the crypto systems. Right. So it was always clear that the first practical application of quantum computers would have to be cryptography, for the simple reason that those actions would happen well before the quantum computer was scaled enough and powerful enough to actually solve the problem.
We are like exploring this gap between when the cryptography system is broken and when the new cryptography is implemented.
Well, okay, so I'm no expert on these aspects of the thing, but I can tell you a few things that are relevant. You know, so the one thing is that it takes a considerable amount of time also to roll out a new crypto system, even after it's fully implemented. On the other hand, there's also some amount of, one has to be careful in rolling out a new crypto system, in the sense that you have to test it very carefully. You have to be pretty, confident that it's not going to be broken, either through classical means or quantum means. Yeah. And, we know quite a bit about these crypto systems, but we don't know everything. For example, do we know that, is it possible that we might have algorithms that attack LWE and break it? It's still possible. It's unlikely, but it's still possible. But then, in order to implement these crypto systems, there are many. You have to implement variants of them because they have to be particularly efficient. And can those variants be attacked? Is there some vulnerability there? So, it's not an envious task to actually make the decision to roll it out. And I think NIST did a wise thing by on the one hand rolling it out, on the other hand saying, well, this is preliminary, we are not yet requiring it. I think that was a very judicious thing to do.
What is your general idea around this new form of math that we can, it's a kind of a new wave of math, also historically in a way. And we learned before that when you discovered the potentials, you really got drawn in it. And what is now, like 20 years after, do you still find it amazing? Do you still discover is now something that's more formalized probably too?
Well, maybe I can still answer that in the context of post-quantum cryptography. Sure. So I think that there's something very, very fundamental about post-quantum cryptography in the context of, there's something that was explored in the context of classical complexity and cryptography, which was this notion of interactive proofs. So proofs we know about from mathematics, but this notion of interactive proofs where proof is something that's written up in a book and you verify it. But what if you had actually a prover who was very powerful, who could prove this to you, right? But now, if you're living in a quantum world, now you can sort of say, look, there's an added element that comes in, because in quantum mechanics, there's what we can see as classical beings, right? So we never see anything in superposition. We don't have direct a direct way of perceiving the quantum world or Hilbert space. Everything comes to us after a measurement, which collapses the state from this enormous, exponentially larger space into just what we can perceive. And so we could think of the quantum world as a prover who's extremely powerful. And is extremely powerful because, for example, you can factor in quickly. Okay, so this entity, of a prover who's trying to prove to you, which was a mythical creature in classical complexity theory, now becomes a physical entity, right? When we are doing an experiment, we are actually interacting with this extremely powerful entity.
Yes, that's
and so the question is, but then what's to keep this entity honest? How do we actually how do we do an experiment and are confident that we really understood the right answer? How did we? And so this is where post-quantum cryptography comes in. So if you have an interaction between a verifier who's much more computationally bounded, much weaker, can only think, has limited capacity, and then you have the prover, which is nature, and nature is much more powerful. How do we do science? How do we understand this entity that's so much more powerful than us? And so this is where you can hope to use cryptography, in doing this interactive proof. What we can hope to do is make use of post-quantum cryptography and interact with the quantum system in such a way that if that if the answer checks out, it's going to be happening inside the cryptography, which even the quantum computer cannot break. So it gives us a level of guarantee about our understanding, which we wouldn't otherwise be able to obtain. And so this is a sense in which, this is something that if you were just thinking about quantum mechanics as a physicist, you would not even imagine, because this is a concept that comes from cryptography, and it's used in this context.
There's nothing like a direct application to actually expose some of the more interesting aspects of a framework of a system, right?
Yes.
This is absolutely beautiful. I love it. The quantum cryptography could be a mediating language to allow us to understand, are we asking questions correctly of the undefined universe around us? And we don't see the calculations, we only see the rendering. And if we understand what we expect to get back, at least we know then that we are framing things in a way we might take the next step forward. That's fantastic.
Yeah. Well, at the same time, there are a number of assumptions from the old math that can be destroyed in a way. So, I mean, even the question of factoring the prime numbers, for instance, but that's one thing, but there might be many others.
We don't even know.
We don't even know.
It might be complex problems actually weren't, but we didn't know how we were framing the measurement or something, right?
Yeah. And concerning that, because you come from the world of math and the education of it too, so do you think this will be a new wave also for teaching and learning math at one point, because it's such big new thing? So it's like
I can tell you about two things there. Many years ago, I think about at least 12, 13 years ago, I taught. This was in the early days of MOOCs, maybe a year after the first big MOOC. I made a MOOC on quantum computing. It was an introduction to quantum mechanics and quantum computing, and it was very interesting. At that time there weren't many courses in quantum computing in most universities, And so there were, there were a large number of people who signed up for the course, I think about 25,000 people around the world.
Cool.
But that 25,000 is not really, not everybody signs up to take the course. They are just curious.
Yeah.
So the first lecture, about half of them watched, so about 12,000. The first homework, about half of them did, so it was about 6,000. And then halfway through the course, it was only 6,000 were watching and 3,000 did the homework. And by the time we finished the course, about half of that number, so about 1,500, actually got a sufficiently high grade in the course that they were given a certificate. Which meaning that they did well in the course and they understood the material and so on. But at that time, even 1,500 students was larger than the number of students who had taken quantum mechanics. But now the interesting thing was, among these students, there were all kinds of students. There were undergrads, there were postdocs, there were even faculty, but there were also people who were just out in industry. There were people who were very old. There were some people who were in their 70s and even 80. And there were some people from high schools and schools. And some of them, I actually, they wrote to me and, I understood who they were. And these were students who were, some of them were bored in their classes. And some actually were not understood in there, so they were very smart, but their math and science teachers did not understand. They were just too, they wanted something different than what they were getting in school. Now there's an effort. There's a non-profit, I think, called Qubit by Qubit.
Okay, cool.
And it was started by a couple of students, including Francisca, who is my PhD student now. She did this when she was an undergrad at MIT, and there's now there's now a group of people who run this, and it's become quite big. And they create these courses for. Online courses for teaching quantum computing, quantum mechanics in schools in various settings, and they have been extremely successful. And I think this is I think a big challenge in education is inspiring students, because if you can inspire them, then there's a lot of energy that gets released, and you can get them to do, in some sense, that's the most important thing.
These are hard things to overcome in terms of regaining a true understanding that will let you move forward. So you need the energy, you need something other than getting a score that passes. You need to be motivated internally by something, and if someone is inspired by something, they will on their own find a way to arrive at. Right. Yeah.
So one of the most interesting things, one of the most inspiring things that for people is paradoxes, right?
Yeah.
If you understand that reality behaves a certain way, which this is why magic tricks are so fascinating, right? And that's true about science and math. It's the magical nature of it, and quantum mechanics is,
it's got a lot in it.
It has an embarrassment of riches there. The problem often is that those treasures get hidden inside a lot of formalism, and so one of the organizing principles of my MOOC was that I used at that time, people talked about this Kanban. Well, actually, it was something that was very that people used to talk about in the 1990s, I think, when the Japanese, method of
Action system. And
just in time,
yes,
just in
yes,
time,
just
right?
in time for
Right. So you don't have to keep a lot of inventory, and so I thought of it as, I wanted to use a Kanban approach to teaching quantum mechanics, and where I wanted to make sure that that I chose the material so that the paradoxes were upfront. So I talked about the Bell inequality in the second lecture. And this was to students who had no background in quantum mechanics at all. But the point was to do it, one, there's the language of qubits and quantum gates makes it easy to do that.
Yeah.
Okay, it makes it much simpler. But second, you can, in the course of that of those lectures, I explained the notion of quantum measurement about 4 or 5 times. So each time, I would refine the notion and use more mathematics. Yeah. So I wanted to make sure that when I first said it, it was as naively as possible. So that the paradoxes were there for the students to experience at a very gut level before, and then they would see it with more and more math as we went along. Yeah.
Well, in the future, math will be only quantum math, probably, right?
No, I think there's a lot of other aspects to mathematics.
Change everything. I mean, now, it grew a lot during your career, but if we are thinking about in 50 years from now, it will be completely different. I mean, even this institution, probably everyone will look only at quantum math, probably.
So I wouldn't quite say that. There are a lot of aspects to mathematics.
Right, there are the foundations, but this is a new growing field, probably, right? Yeah.
It'll probably be integrated in ways that we can't even imagine, right? Some fundamentals maybe will settle into an understanding.
Yeah.
The Simons Institute is a pretty unique institution. We have it's a place where people from all over the world come here from theoretical computer science, but also we have this view of the computational lens, computation reaching out to all the sciences, and including of course, social sciences and economics as well as the hard sciences. And the quantum research pod here is a interesting. We started with a couple of research pods which provide a number of researchers, postdocs, visitors who are here on an ongoing basis, and it's been a very interesting, kind of a unique program to bring people together. Also to have this deep interaction with the rest of computer science.
You've had so much with randomness in your thinking and into your publications and everything. So, on randomness being perhaps a safe space for all, seems to be in just all sets of data and everything, there seems to be a small percentage that is always very difficult to fit with everything else if you squeeze the bounds a little bit too much. Any thoughts on randomness and randomness within there's a certain portion that you could say is kept aside, even in these computational systems that have something beyond us?
So this issue of randomness is really quite fascinating, and randomness in quantum mechanics, even more so. There's the famous quote of Feynman, of Einstein, who said, "God doesn't play dice with the universe." He really did not like this notion.
Oh yeah, exactly.
And was it Niels Bohr who said, who retorted, "Don't tell God what to do
I
with
think
it."
it was Bohr, yeah, and I think that's very funny exchange.
Yeah, yes.
Because,
But-
well, that is the better way to look at it.
But there's so this post-quantum crypto sort of comes into this in very interesting ways. Again, there's this whole issue of certifiable true randomness,
Yeah.
right? So
Yeah.
so the question is how can you, on the one hand, quantum mechanics, the laws tell us that whenever you measure, you get the outcome is randomly picked from a certain distribution.
Mm-hmm.
And that's true randomness. That's the source of true randomness in the universe. But now suppose that you wanted to, suppose you wanted to build a device that generated true randomness.
Mm-hmm.
How would you know? How would you know that it was
Yeah.
it was truly quantum inside?
Yeah.
How would you know that it was calibrated properly
Yeah.
and something didn't go wrong?
Oh, what if the measurement
Yeah.
itself has something with a noise floor,
Yeah.
noise floor detection problem, and always has a bias?
Right.
Exactly.
So this is a question that that we worked on, a lot of us, and it turns out that what you can do is, again, there's this way, when I talked about a verifier and the quantum system.
Yeah.
So you could look at this the same question with the notion that now you have a system, quantum mechanics, that's generating true randomness for you. But how would I be convinced that it's real randomness?
Yes.
Right?
Yes.
And so there's a way of using post-quantum cryptography to sort of hide the true meaning of questions that are being asked
Yeah.
to the quantum prover
Yeah.
in such a way that if these, if the answers pass certain tests, then in fact you can be sure that what's being given is truly random.
Yeah.
And so you can invest a small amount of pseudo randomness. I can start with a small amount of true randomness, encapsulated within these post quantum cryptography. Use it to interrogate you as a quantum system.
Yeah.
And now, as long as you're unable to break the post quantum cryptography during this interaction. It doesn't matter if you break it afterwards.
Yes.
As long as you're unable to break it during this interaction, I can be sure that what I have received is true randomness. It was fresh randomness. It was generated right then. You could not have generated it before and stored it. And that this randomness is inaccessible to anybody, including if there's an adversary you share entanglement with, that adversary would not have access to this randomness. So this is something that in a classical world we had no right to expect. But so when I worked on my PhD dissertation, it was on minimal assumptions to generate randomness in a classical world, and so there, there were, that whole line of work showed that there were rather minimal assumptions under which you could generate randomness, but those minimal assumptions involved, you had to assume things about sources and independence and so on. And if you violated them even a little bit, there was no possibility of generating randomness, including in this situation where you were interacting with one device, It was just impossible to generate true randomness or any extra randomness. And so to have this happen where you could certify that something was truly random, this was an
fantastic.
Yeah.
You were primed for that situation, and you knew it when you saw it too, right?
Yeah.
It is going to be very interesting to have something like a feedback or sounding board that we can use to say, during this time-bound interaction, we know that we had calibrated and had every reason to believe that we had. Yeah, it's fascinating.
Yeah.
It's fascinating.